Right, in this video here, I'm going to plot a linear graph, a graph of a linear relationship, and I'm going to write a graph equation for the graph after I've calculated the gradient. Okay, so here we're plotting two variables, force against extension. So first thing I do, I'm going to put force label, put the unit on the y-axis, and here's extension, which is x. Just so happens that the value for this extension is x, and it's on the x-axis. It's measured in meters. I'm going to put it there. I'm going to come up with an appropriate scale for my force. I'm going to start my force about here. So I'm going to put 0 here. I've got about 20 boxes up there, and the force goes up to 3. So let me say 4 newtons. So I'm going to go 5 boxes every 1, 2, 3, 4, 5 for every 1 newton. 1, 1, 2, 3, 4, 5. 2, 2, 3, 4, 5. 3, and 2, 3, 4, 5. It's 4. Okay, so I'm going to do the same thing, make a scale on this side. There's about 34 boxes along, and I go up to about 0.15. So if I mark off every 2 here, that's going to give me about 0.01 for every of these. But actually, let's do every 4 because it's going to take me a long time. So I'm going to start off with 0.02, 0.04, 0.06, 0.08, 0.10, 0.12, 0.14, and 0.16. Okay, so now I've got my two axes. Scales are nice and even. They're labelled, so I'm going to go ahead and plot the points. Our first point is extension is 0, and the force is 0.49, which is going to be about here. I'm just going to do this quickly. The next one is extension 0.23. Oh, sorry, 0.023. So this is 0.023 is along about here, and we're going to plot this about here. 0.049 and about 1.47. 1.47 about there, 0.74, 74, and 1.96. Is that right? 0.74. 74. Okay, and 102. I'm trying to do this quickly, and it's a wee bit rough, but that's all going to come out in the wash when I do my line of best fit, because it will sort of minimize the errors. If you want to take more time, which you should, that's fine. I'm just quickly demonstrating this next point about here. Okay, and the last one, 1.54 and 0.43. So we're going to go about there. Sweet. So now what I'm going to do is I'm going to draw a line of best fit. Now, when we draw a line of best fit, really important that we try and get our points evenly balanced on both sides of our line. So let me just pretend this is an edge of a ruler. So you can see there, that's a reasonable balance. So I've got, you know, this one's above, this one's above. You know what, maybe I could just tweak that one a wee bit better there. So that's a wee bit above, just on, below, below, above, below. So that doesn't look too bad there. That's my line of best fit here. So there we go. Okay, let's just call this LOBF. Okay, and now what I'm going to draw is, I actually want to find the gradient of this line. So I'm going to choose 2 points on the y-axis here. I'm going to go 1 and 3, and I'm going to find out where they intersect the line. Again, I'm going to use this, and I think I'll use a blue color. So let's put this at 0 degrees. So we get a nice horizontal line here along the 3. There we go. So I always like to just dash this one so I can just tell that it's different. You might not always be able to do this in different colors. So I'm going to go along until it just intercepts. Okay, and then while we're at it, we might as well do the one that's at 1. Here we go. Till it intercepts, which is just there. Rotate this around again. Let's get it at 90. What have we done there? Okay, 90. So let's get that right on that intercept line there, which is quite lucky. That kind of goes on one of these ones. Okay, and then along to this one. Sweet. So this bit here, from all the way to here, okay, this is our change in y, from all the way from here to here. Oh, sorry, that's a pretty messy arrow there. This is our change in x. Okay, and whenever we want to work out gradient, and of course gradient when we're doing graphs is equal to m, and m, the gradient, is equal to the change in the y over the change in x. Now in physics, just to make sure that we get our error is as small as possible, we try and take a big section chunk of this line, at least half, and we're looking for 2/3 of this line. We're not just going to take a small sample. So we've got m equals change in y over change in x. So let's look at the change in y. It's 3.0 newtons minus 1.0 newtons. Okay, over x, which is what? 1.23 minus 0.225. 0.123 minus 0.2. Oh no, that's 0.25. 0.025. This equals 2 newtons over 0.098. And just let me get my calculator out here, and we're going to get the answer of 2 divide 0.098 equals 20.40. I'm just going to round that up to 20.4 newtons. It looks like an approximate answer here. So this is our gradient. Right, now let's put this gradient into a graph equation. So here's the generic form of a graph equation, which is y equals mx plus c. Y here is our variable on the y-axis, m is the gradient that we just calculated, x is the variable on the x-axis. In this case, the value on the x-axis actually is x for extension, and c is the intercept on the y-axis. So if we use algebra, we can substitute these straight in. So let's put in f instead of y equals, put the gradient for m, including the units, which are meters per newton. Sorry, newtons per meter. Let me just change that. Here we go. Newtons per meter. then we get the c-intercept, which is 0.47. That is the graph equation for this graph, for this linear graph. As this is a linear graph, we've also got a relationship here which says that that f is directly proportional to x. That is, if we increase x by any number, f is going to go up proportionally, which is what the straight line means here. So let's just double check what we've learned in this video. First thing is we learned how to set label and axis and put an appropriate scale for the units that we have. We've then plotted the points, drawn a line of best fit that best fits within the point, found the 2 points on this line of best fit that are at least halfway along the line, or at least halfway of the line, which we can calculate the change in y and the change of x to put into our equation over here to calculate our gradient, then substitute our gradient into this graph equation, this generic form here, to make a specific graph equation that we've now got for this graph. I hope this has been helpful for you to practice working out how to derive a graph equation from data. Thanks very much for listening.